Welcome, everyone. Today, we'll be covering important database concepts and SQL fundamentals that are essential for test leads. Whether you're new to databases or looking to strengthen your understanding, this overview will help you grasp the key ideas and terminology you'll encounter when working with data in testing environments. We'll explore how databases store information, the basics of SQL queries, and how this knowledge supports effective test planning and execution. This foundation will make it easier to validate data, troubleshoot issues, and communicate with developers and database administrators confidently throughout your testing projects. We'll start by looking at the basics of databases and relational database management systems, which form the foundation for managing data efficiently. Then, we'll explore key database entities and the constraints that help maintain data integrity. Next, we'll introduce SQL, the language used to interact with databases, and discuss its various applications. After that, we'll dive into the core SQL statements, including data definition language for defining structures, data manipulation language for handling data, data control language for permissions, and transaction control language for managing transactions. We'll also cover database programmatic objects like procedures, triggers, and functions, which automate and extend database operations. Finally, we'll compare the drop, delete, and truncate commands to clarify their differences and appropriate use cases. This overview will set the stage for a deeper understanding as we proceed. Now, let's focus on understanding what databases are and how relational database management systems, or RDBMS, work. This will give us a solid foundation before we dive deeper into specific database entities and SQL commands. We'll explore the basic concepts behind storing and organizing data, and how RDBMS help manage that data efficiently through structured tables, relationships, and rules that ensure consistency. This understanding is key for anyone working with databases, especially when writing or testing SQL queries. Databases organize data in a structured way so it can be stored electronically and accessed easily. They allow multiple users and applications to share and retrieve data at the same time, which makes collaboration and efficiency possible. A key role of databases is to ensure that the data remains consistent and accurate, which is essential for reliable business operations. Modern databases are also designed to handle large amounts of data, support many users working at once, and recover quickly in case of any failures, ensuring continuous and dependable service. Relational databases organize data into tables made up of rows and columns, where primary keys uniquely identify each record and foreign keys create links between related tables, ensuring organized and connected information. This structure supports data integrity, allowing accurate and consistent data storage, and enables complex SQL queries that help retrieve and manipulate data easily. RDBMS systems are also scalable, adapting to growing amounts of data and manage multiple users working on the database simultaneously without conflicts. These capabilities, along with their reliability and maturity, have made RDBMS products like Oracle, MySQL, and SQL Server leaders in the database market. The image here highlights the concept with example tables and keys, illustrating the relationship and how queries use these keys to fetch specific data efficiently. The core components of an RDBMS include the database engine, which handles storage and retrieval of data, the query processor, which interprets and executes SQL commands, the transaction manager, ensuring data consistency and handling concurrent database operations, and the storage manager, responsible for efficient data storage. In a client-server model, users send queries through a client interface that reach the API or web server, which then interacts with a load balancer, distributing those queries to multiple database servers for processing. The system also uses in-memory caches to speed up data access, while mechanisms like replication keep data synchronized across servers for reliability. Data flows through these components, moving between storage systems, caches, and backup units, with indexing and search services enabling quick data retrieval. The entire process from query submission to result delivery is coordinated through a query execution pipeline designed to maintain performance and data integrity while monitoring tools oversee system health and disaster recovery measures protect data against loss. This architecture ensures that data is stored, managed, and accessed efficiently and reliably. Next, we'll focus on the key components that make up a database, its entities, and the constraints that ensure data remains accurate and reliable. Entities represent the main objects or concepts in a database, such as customers, orders, or products, usually organized into tables. Constraints are rules applied to these entities to maintain data integrity, for example, ensuring that primary keys uniquely identify records, foreign keys link related tables correctly, and that certain fields cannot be left empty. Understanding how entities and constraints interact is essential for designing a robust database structure that supports consistent and meaningful data storage. In a database, tables are used to represent entities, which means they organize data into a clear, structured format that's easy to understand. Each table consists of records, which are the rows that hold individual examples of that entity, so each record is a unique item or person in the database. The columns in the table are called fields, and these define the specific attributes or details about each record. For example, in the table we see here, each row is a record representing a person, and the columns include attributes like ID, name, age, email, and join date. This way, you can quickly find specific information about each record by looking at the relevant fields. This structure makes it easy to store, retrieve, and manage data logically within the database. A primary key uniquely identifies each record in a database table, ensuring that no two records are the same. This is crucial for maintaining clear and accurate data. The foreign key plays an important role in linking tables by enforcing referential integrity, which keeps related data consistent across different tables. Unique constraints prevent duplicate values in a column, while check constraints make sure the data meets specific rules set for that column, like limiting the range or type of values. Lastly, the not null constraint requires that certain columns always have a value, preventing empty or missing data where information is mandatory. These constraints together help keep the database organized, reliable, and accurate. Here we see an example of an entity relationship diagram that shows how data is structured within a database. The diagram uses boxes to represent entities like customer, order, and product, each containing key attributes such as customer_ID, order_ID, and product_ID. The diamond shape labeled places indicates the relationship between these entities, showing that a customer can place multiple orders while each order can contain one or more products. The numbers on the connecting lines represent cardinality, clarifying how many instances of one entity relate to another. This kind of visualization is valuable because it helps you understand how tables are linked through primary and foreign keys, how data integrity is maintained, and how constraints shape these relationships, which ultimately supports effective database design and ensures data is organized logically and efficiently. Now that we have explored how entities and relationships are structured in a database, let's shift our focus to SQL, which stands for Structured Query Language. SQL is the standard language used to communicate with and manage databases. It allows us to create, read, update, and delete data, as well as define the database schema and control access to the data. Understanding SQL is essential because it provides the tools needed to interact with the tables and constraints we've discussed, making it possible to retrieve meaningful information and maintain data integrity within the system. This introduction will help us see how SQL fits into the overall database environment and its practical uses in managing data effectively.
SQL is the standard language used to work with relational databases, allowing us to manage data effectively. It lets users perform key operations like inserting new data, querying existing data, updating records, and deleting entries, all through straightforward commands. These functions, often called CRUD operations, help keep the data organized and accessible. Beyond these basics, SQL is essential because it supports complex data manipulation that businesses rely on for daily operations, generating analytics, and even testing software. The image here shows how SQL links tables by matching user IDs in one table with orders in another, demonstrating its power in handling relationships within databases. This capability is crucial for making sense of data across different parts of a system and extracting meaningful insights quickly.
SQL plays a key role in testing and development by helping ensure data accuracy and integrity after database transactions, which is essential for reliable back-end operations. It also assists in preparing and managing test data, making it easier to set up various testing scenarios. Automation of database testing is another important use, where SQL scripts streamline regression and data-driven testing, improving efficiency and consistency. During development, SQL is widely used by developers to manipulate data and identify issues related to database operations, allowing quick debugging and smoother application performance. The setup shown here illustrates how queries and test results work together to track and verify database states, highlighting both successful validations and areas needing attention. Here we see examples of SQL queries and their results, which help illustrate how data is retrieved and manipulated in a database. The select statements on the screen pull specific columns from a table, filtering rows based on conditions, like querying users older than 30, and ordering them by age in descending order. This allows us to focus on relevant datasets efficiently. Below that, another query aggregates sales data by product, showing the total sales amounts clearly grouped by each product category. These examples highlight how SQL syntax works, providing a clear structure for forming queries and interpreting the output. Additionally, when it comes to modifying data, statements like insert, update, and delete change the contents of tables, with their results confirming that these changes have been successfully applied. Seeing these real-world query examples side by side makes it easier to understand both querying and data modification tasks in a practical way.
Next, we'll focus on the core SQL statements that form the foundation for managing and controlling data within a database. These include Data Definition Language, or DDL, which handles the creation and modification of database structures. Data Manipulation Language, or DML, which is used to insert, update, delete, and retrieve data. Data Control Language, or DCL, which manages permissions and access controls. And Transaction Control Language, or TCL, which ensures the proper execution and integrity of transactions. Understanding these categories will help clarify how SQL commands are organized and applied in different scenarios. Data Definition Language, or DDL, statements are used to define and modify the structure of database objects. They are key to managing the schema, which is essentially the blueprint of the database. The main DDL commands you'll encounter include create table, which sets up a new table with specified columns and data types, alter table, which allows you to change the structure, like adding a new column, and drop table, which deletes a whole table. These commands play a crucial role during the initial setup of the database and whenever the structure needs to be updated. However, it's important to note that DDL commands don't manipulate the actual data stored in the tables. That's handled by other SQL commands designed for data operations. Data manipulation language statements include 4 main commands used to interact with data in a database. Select queries let you retrieve and view data from tables, which is essential for reading and analyzing the information stored in your database. Insert statements add new records to these tables, allowing you to grow and update your dataset as new data becomes available. Update commands are used to change existing data entries when you need to correct information or reflect recent changes. Finally, delete statements remove records that are no longer needed or are incorrect, helping keep the database clean and accurate. The image here shows this process visually, with arrows illustrating how data moves between tables and the results depending on the command used, emphasizing the dynamic flow of data manipulation in databases. Data Control Language, or DCL, deals with managing access and permissions within a database using commands like grant and revoke, which help keep the database secure by controlling who can do what.
On the other hand, Transaction Control Language, or TCL, focuses on managing transactions with commands such as commit to save changes, rollback to undo changes, and savepoint to create checkpoints within a transaction. These commands play a critical role in multi-user environments by ensuring data consistency and reliability, allowing different users to work with the database confidently without causing conflicts or data loss. The image here highlights these two key aspects. The lock icon represents security and access control through DCL, while the arrows, checklist, and coins symbolize transaction management and data integrity maintained by TCL commands. Together, DCL and TCL form essential tools for maintaining order and trustworthiness in database operations. Next, we'll take a closer look at three important types of programmatic objects in databases: procedures, triggers, and functions. These objects allow us to encapsulate logic directly within the database, making operations more efficient and consistent. Procedures are sets of SQL statements that can perform tasks like inserting or updating data and can be called as needed. Triggers automatically execute in response to specific events, such as when a row is inserted or deleted, helping maintain data integrity or enforce business rules. Functions, on the other hand, return a single value and can be used in SQL statements to perform calculations or manipulate data. Understanding how to use these objects effectively can greatly enhance how we manage and interact with database systems. Stored procedures are sets of SQL commands that are pre-compiled and stored within the database to handle repetitive tasks more efficiently. Because they are pre-compiled, they reduce the time the database needs to parse and execute queries, which leads to better performance. They also help improve security by encapsulating business logic inside the database, preventing direct access to data, and controlling how users interact with it. Common uses include validating data before it's saved, processing large batches of records, and enforcing specific business rules centrally within the database, which helps maintain consistency and reduces errors. Triggers are automated procedures that run in response to specific events in a database, such as inserting, updating, or deleting records. They help ensure that business rules are consistently enforced without the need for manual intervention. For example, triggers can automatically update a timestamp whenever a record is changed, keep detailed audit logs for tracking user actions, or prevent unauthorized or invalid changes to data. They also play a key role in synchronizing related data across different tables or systems, making sure everything stays consistent and up to date. The image here illustrates these concepts with automated procedures connecting different databases, audit logs tracking activity, and synchronization between separate data sources. This helps maintain data integrity and simplifies management tasks within the database. Functions are routines that take input parameters, perform specific operations, and return values that can be used elsewhere in programming or database queries. Unlike procedures, functions always return a result and can be included within SQL expressions to make queries more dynamic and effective. They are commonly used for calculations, such as applying discounts, or for formatting and transforming data, which helps keep code modular, reusable, and easier to maintain. For example, a function might fetch data based on given criteria, process that data, and then return it for further use, streamlining complex operations into a single callable unit. This approach not only simplifies coding, but also enhances organization and efficiency in managing database tasks. Next, we'll look at the differences between drop, delete, and truncate commands. These are all used to remove data or database objects, but they work in distinct ways and have different impacts. Drop removes an entire table or database object permanently, including its structure and data. Delete removes rows from a table based on a condition, but retains the table itself. Truncate quickly deletes all rows in a table without logging individual row deletions, which makes it faster but less flexible than delete. Understanding when and how to use each command is important for managing data safely and efficiently. The drop command is used to permanently remove entire database objects, such as tables, including all their data, and this action cannot be undone. In contrast, the delete command removes specific rows based on conditions and allows for rollback within a transaction, making it safer when you want to modify data without losing everything. Lastly, the truncate command quickly deletes all rows in a table by not logging each individual deletion, which makes it faster than delete, but it often cannot be rolled back, so it should be used carefully. The image illustrates this well by showing tables being thrown into trash to symbolize drop, a delete button removing a specific user record, and a spray clearing all data at once to represent TRUNCATE's rapid clearing ability. Each command serves different needs depending on whether you want to remove data partially, completely, or swiftly. The drop table command completely removes a table from the database, including its structure and all data, and this action is permanent with no recovery option. In contrast, the delete command only removes specific rows based on a condition, leaving the table itself intact and allowing for transaction control, such as rollbacks. The truncate table command quickly deletes all rows in a table but keeps the table structure, which makes it faster than delete when removing all data. However, unlike delete, truncate cannot be used with a where clause and usually cannot be rolled back in many database systems. These differences also affect performance. Drop and truncate are generally faster than delete for large datasets because they don't log individual row deletions. When choosing which to use, consider whether you need to preserve the table, the ability to recover data, and the speed required for your operation. The drop command completely removes the entire table along with all its data, leaving nothing behind, as shown in the top part of the image where two tables disappear entirely. In contrast, the delete command removes only specific rows from a table based on a condition, but keeps the table structure intact, which you can see in the middle section where the table remains but its contents have been deleted. The truncate command works differently by quickly clearing all rows from the table while preserving the table structure, optimizing performance for bulk deletion. This is depicted in the bottom part where the table is empty but still present. Visualizing these before and after states helps clarify the impact each command has on database integrity and recovery options. Mastering databases and SQL is a key skill that supports effective test leadership by enabling clear communication with technical teams, understanding data structures, and designing precise test cases. With a solid grasp of commands like drop, delete, and truncate, and knowing how functions work, you can lead testing efforts that are both efficient and reliable. This knowledge helps in anticipating how data changes affect applications, ensuring tests cover critical scenarios, and ultimately contributes to delivering high-quality software. Building these skills empowers you to guide your team confidently through complex data-related challenges and make informed decisions throughout the testing process.